Strange.
What sort of image?
It says like video 360.
Oh, well, that guy.
Yeah.
No.
Walk off with myself, did I?
We actually didn't end up watching.
That's
just like talked for 2 hours.
Nice.
Awesome.
We have nothing else.
Wow, you should have. That was a kind gesture.
Yeah, of course. No, it's like,
Thanks.
right, I hadn't boxed it up because I wanted to show you a trick with it, but you didn't.
Sorry.
No, it's okay. But I was thinking, why didn't I box it? Because I was hoping George would come down.
Right. Could be worse.
Oh, some of those. That's it's the home. That's awesome. We pick up our folders or?
Oh, sorry. Yeah, that's a fair question. It's good. So, yes.
Yep.
Dude.
I'll wait for the.
Yeah.
And there's some snow. There's some.
Starting again, so we were using Cyrus.
You told me.
Just as I'm not going wrong.
Yeah, I am.
It's very.
Shaking you up.
No, it's just that
I'm not
No problem.
Yes.
I didn't know that they did that like so many times during the show.
Do you think we want to go after?
And then.
Well, my Thursday night come over, we'll pass it. Okay, yeah, but I'll add this.
Fridays are the best.
What do you have? Strong.
And then it's very.
Alright, so we talked about last time.
So stupid.
Last time we were talking about angular momentum. And we said if you're dealing with a spinning object, it's better to use L equals I omega. If you're dealing with a point mass moving, then it's better to use R cross P. We also talked about the relation with torque. So just like we have F net equals dP dt, we have tau net equals dL dt. And torque is the rate of change of momentum. And so similarly, the force, the second law in terms of force and momentum told us that if F net external equals 0, then P system initial equals P system final. And so similarly, if tau net external equals 0, we have L system initial equals L system final. And we've seen some examples of that with the neutron star and the bigger skater, and we've seen that angular momentum is conserved in those cases, and we can use it to figure out the behavior of the system. Okay, so let's talk about well, actually, so that I don't forget, let's do a couple of the demos right in the beginning. So we've seen one of them, but if anyone wants to do a repeat or reboot of Avi's performance, yeah, sure, Nate. Okay. All right, so get off the platform. Hold on to the yeah. All right, yeah. Put it. Don't sit on it. Yeah. Put it. Yeah. Tension between your thighs. Right, and then start with them up close against your chest, and I'm going to spin you up, and then once I let go, you can like slowly put your hands up, and then bring it back in. Right. So that's really hard to balance. All right. Oh yeah, and you can see once he brings it in, the speed goes up again. Okay, now the friction has taken hold. Oh, okay, it's still there. Let's see, one more time if you don't mind. Okay, I mean, I'll spin it up, yeah. There.
What's up? There you go.
All right. It does get you dizzy. Okay, all right, yeah, no, I think the friction was a bit higher. Yes, okay. All right, round of applause for Nick. Okay, so what we saw there was changing the rotational inertia, right? There was actually some external torque because there was some friction there, and but in the case when this doesn't have as much friction at the axle, then basically Nate would keep spinning, and depending upon the moment of inertia, his omega would change. When his I was large, his omega would be small, and vice versa.
Where exactly was the?
Oh, at the axle, it's not a perfectly frictionless axle, and so well, you can see already when I start this spinning, like well, right now it's okay, but when you put more weight on it, you can see it's slowing down already. So it's not a perfectly frictionless axle. It should ideally just keep spinning once I start. Okay. One more demo using this. Someone else volunteered. Yes. Lauren.
Wait, now I'm scared.
All right. So go ahead and I'm gonna need actually Max, you can help. So well, actually, let's stand to the side for a moment. All right. What I'm going to do, let me explain. I'm going to spin up this bicycle wheel and hand it to Lauren. Okay. Yes, you can hold on. Which way do you want the angular momentum pointing, up or down? Up to you. Up, okay. So if we want pointing up, then the right-hand rule tells us that it has to be spinning this way. All right. So, okay, go ahead and spin it up, and I'll make sure to give it to Lauren in the right direction. So spin it up a bit more. Okay. And so, no, there, that's right. Now that's down. Okay, I'm going to give this to you. So hold it like this for the moment, and then flip it 180. Okay, and then flip it 180 again. All right. So, yeah, that was pretty much the demo, but thank you. It's cool, right? It feels weird, yeah. Yeah. All right, I'll take this off your hands. Yes. Thank you very much. We're around for a lot. Okay, so what was happening? Anyone want to take a stab at explaining? Yeah, Nick.
Can you say like angular momentum was added to the system
When?
when Lauren grabbed the spinning wheel?
Sure. And then I mean that's fine. And she grabbed it and she was just initially just staying stationary, holding it like that.
And didn't transfer any.
It didn't transfer any. And then when she flipped it, she started spinning. Why?
The direction changed.
And so, but why does that lead to her spinning? Yenta.
Angular momentum had to be conserved, so if you switch this kind of change directions, then the first one also has to change direction.
Basically, yes, yeah. The total angular momentum needed to stay the same, yes. So when the wheel had, so the system became Lauren plus the bicycle wheel, right? And so initially the angular momentum of the system was pointing up, okay? But then what happened? Lauren turned it, so the angular momentum of the wheel was pointing down, but the system's angular momentum needed to stay the same. And the way to resolve that was that Lauren and the system as a whole started rotating the other way as to keep the total angular momentum pointing. Yeah, and yes.
Why didn't Lauren start spinning as soon as they like took the bicycle wheel? Because now like the angular momentum just changed. Because without a bicycle wheel has something, and then with the wheel, there's now a different momentum.
Right, but what's your system?
Oh, I guess it's Lauren and the bicycle wheel.
Exactly, yes. So if your system is Lauren and the bicycle wheel, initially accepting the bicycle wheel, there's no change there. The bicycle wheel has the angular momentum, And then now it's Lauren bicycle wheel overall has the momentum and it's localized in the bicycle wheel. Yes, Adi.
If one were to draw a free body diagram of Lauren and the bicycle wheel, would one say that, like, where would the force, I mean, I know that Lauren and the wheel are like a system, so like they're maybe like internal
Yep.
forces inverted, but like what would the force back, like arrow look like, I guess? Like, is the force coming, like being exerted on Lauren by the wheel, or because it's like a system, that's like not how it works, or?
Oh, I see. Yes, it's an internal transfer of angular momentum. So it's like when you have a collision and like angular momentum transfers from one to the other. And so in the process of, well, Lauren had to exert a torque actually on the wheel to turn its L upside down. And in the process, the wheel exerted a torque on her.
Interesting.
It's starting to rotate. Yes.
So then why, when I tilted it back to the original position, did
Good
it
question.
not
Yes.
become zero again? Or can I not put angular momentum back into the wheel? Or maybe the system has lost like energy, so I have to keep spinning more.
You're getting closer there. Yeah. Speculation?
Is it due to friction?
It's basically, yeah, so there was like the wheel had lost some of its spinning speed,
Yeah.
right? But there was still not that much external angular torque, right? So when you flipped it back, it still wanted the total torque to stay the same, but now the wheel wasn't contributing quite enough. So you still needed to spin a little bit.
Yes. So the perfect system, I would flip it and I would go around positively and then
Flip it back and you would stop, yeah. Other questions? Let me ask, let me ask this. So with the ice skater demo, right, or with Nate, when Nate pulled his arms in, he spun faster, right? And we know that the angular momentum was conserved. What about the kinetic energy? Let me just give you three simple choices. With arms out, or what the arms in, omega increase. We saw that. And then A, you can say K rotational increase, B, K rotational stay the same. And C, K rotational decrease. Take a moment to think and like pull out your voting cards. This is a quick photo of that.
This says with arms in angular velocity
Increase.
increase.
Sorry, yes, yes.
Increase.
Ask the source, right? Yeah. Okay, so when Nate pulled his arms in, we saw that his omega increased, right? He spun faster. And the question is, what can we say about K rotation? Okay, you want any more time? All right, then show me. Oh, sorry. Okay. Most people for B stayed the same. No, the kinetic energy actually increased. Yeah.
Oh, yes.
Omega squared, but yes, yeah, yes.
If we're talking about it from like a work perspective, where it's like, what's providing the force?
Excellent question. Yes. So first, let me sort of convince you that omega did, not omega, that kinetic energy did increase, and then yes, we'll talk about Aiden's question, which is where did that energy come from? K rotational, what's the formula? 1/2 I omega squared, all right? And so both I and omega are changing, right? So it's not as simple as saying that, oh, omega increased, therefore K rotation increased, because I actually decreased, right? But one can argue that, oh, it's omega squared versus just 1 power of I. A more rigorous way, though, would be to look at another formula for K rotational. So just like K translational, we had 1/2 mv squared, and we also had it as p squared over 2m, right? Just recasting v in terms of p. So what would be the corresponding formula for K rotation?
L squared. 2i.
2i, exactly, yes. L squared over 2i. And this makes it clear that yes, L was conserved, so L stayed the same and only I changed, right? So it's even clearer than arguing from 1/2 I omega squared. L squared over 2i, L stayed the same, I decreased, and so the rotational energy increased. Okay, so now Aidan's question, where did that energy come from? Yes. Yes, all of them.
The arms and generate work.
That's exactly right. Yeah, it was Nate who supplied the energy. Because the natural tendency of those weights is to like fly off, right? And it's definitely not like natural for them to come in closer. He had to actively do work to bring them in closer. And that manifested as increased omega. Yes.
Also positive.
Oh, they want to work?
Acceleration.
Yeah, he's pulling them in and they are indeed moving in, exactly. So yeah, he's doing positive work and the rotational kinetic energy. Yes.
Could I apply that then to this example where I was spinning, where it took effort and energy work to flip the wheel?
Okay.
So am I applying any work to like decrease the angular momentum of the wheel, maybe through air resistance or something? And could that, rather than friction, decreasing the angular momentum of the wheel? Like, am I doing negative work on this?
Oh, I see. No, I don't think that's the main case there. I mean, there is certainly some friction at the axle, and that is an internal force, which is why it transferred angular momentum like back to you essentially. But no, I mean, you are doing work changing, like you change the direction of L. So, but the sort of the tricky part there is, I think at some point you would be doing negative work and at some point you would be doing positive work.
So then maybe those would cancel out.
I
for
think
the
so, yeah.
system. Okay.
Yeah, leaving the total kinetic energy the same overall.
Okay.
Yeah. Right, because you were basically not changing the magnitude of L, you were just changing its direction.
But Nate was actually like doing work to change the system, like to change the shape of the system.
Oh,
I'm just
okay,
trying to figure out how these two things are different.
that's a fair point. Let me think. I will think about this. Your case is a bit more complicated. I will say actually, one thing you have to be careful about with Nate's case is that, so just like we have the work, so we've seen work energy theorem, and we said, oh, W total equals delta K. And so in the rotational context, we can also talk about work rotational. And while regular work was F dot dr, from initial to final, work rotational would be tau dot d theta from initial to final. The thing you have to be careful about with Nate's case, so here we say, oh, work total is change in kinetic energy, and kinetic energy is 1/2 mv squared. But that's this result holds under the assumption that the mass is not changing. If you try to do something equivalent for the rotational case, it would only be true in the case when I is not changing, which is not true here. I is changing for Nate. So you have to be careful about trying to apply an equivalent work energy theorem for net. Your case is trickier, yeah, I'll have to think about it a bit more. All right, other questions? Yes?
Said the work done was on the direction of acceleration, but aren't they all?
Not in the direction of acceleration. I said that he was exerting a force inward and the masses were being displaced inward. So the direction of his force and the direction of the displacement of the masses was in the same direction. All right. Let's see. Yes.
Suppose he had, instead of going from here to chest,
Yeah.
gone from here to his side.
Okay.
Would that have changed anything? Like, does the distribution of mass up, down?
Up, down, no. Just distance from the axis. Okay, so let me ask a couple of questions. All right, so two objects, same mass, same shape, same speed, move towards each other on a frictionless surface. What happens if they collide head on and stick together? Won't give it too long. Get ready. What do you think? Okay, most of you foresee they stop in place. That's completely correct. Yes, no tricks here. The total momentum is 0. Oh, question, yes.
Sorry, just to go back one more time, because the change on like the momentum of staying consistent, you spin it faster, drop the tongue down to the side, not relevant where they are vertically, it's just on
Right.
one axis. And in that situation, what would be positive work? It's not, would it still like, are his arms still doing anything? Because wouldn't it be gravity that he's just, or
Okay, you can see. So, and then.
You still have to hold your arms up.
You still have to, yeah, yeah, pull them in because the sort of centrifugal tendency is for them to go outward. So, no, I think he's still
doing
doing.
positive work?
Yeah,
Got it.
yeah. All right, so yeah, so total momentum here is 0, and it's a totally inelastic collision. They stick together, final velocity is 0. Okay. What about this case? So don't think of these as point masses, think of them as like slightly larger circles. And they collide, but they're colliding off axis. Anyone need more time? Okay, show me what you think. Okay, mostly for D, since they stick together, they're not going to move perpendicular to the origin trajectory. Mostly for D, they start spinning in place, that is correct. So I think I found the video of it.
Hello, everybody. Just waiting here for this little virtual lab. I'm going to take your video. Which I gave you in the previous kind of video. So the first thing I'm gonna do is come up here where it says int. Not actually 1 meter, this is 3.
Okay, that's not quite the video I was hoping for. Let's see, videos. Maybe this one? Yes, I think so. Okay, that was not sticking together. Okay, that's just, oh, no, that's just the regular momentum collisions. We've seen that before. Hold on, let me see. Declining stick. And then I'll put in angular. Okay. Angular momentum. Solving stuff on tablets. No, okay, sorry. I thought I could quickly pull it up. The sad thing is I completely forgot we have a demo actually showing this. So, but we forgot to arrange it, and it's a bit bulky, so we can't do it quickly. But yes, basically, these two will stick together and then just start spinning in place. You've probably seen, again, they're probably ice skating routines where you've seen them as like they come together and like, oh, they clasp palms and then they like sort of spin together. Sorry? Which direction? Ah, nice question. So let me draw that on the blackboard a little bit bigger so it'll be easier to discuss. So, say we have point A. B. And so this one is heading like that, this one's heading like that, and they collide and stick together. Why do they start spinning? First, let me ask that. I mean, why is maybe a bad question, but is there a way of thinking about it that makes it natural that they would start spinning? Yes, Anta.
In the X direction, we know they'll just stick together, but then in the Y direction,
Okay, all right. Lauren had her up
I
next.
did, but I think that maybe someone else should do.
Sure.
Yeah.
Okay. Yeah.
They're like providing torques on each other.
Okay. Yes. Yeah.
like A goes that way and it sticks to B, but it like wants to keep going that way, so it is just like has more like.
Okay. Yeah. All right. So a mix of those answers.
I think so. I thought about initially when they stick together, now they have a shared center of mass and they are both applying a torque to their shared center of mass because the force is not applied directly at the shared center of mass.
Okay.
So they'll start spinning.
I wouldn't phrase it quite that way, but you're not too far off. Yes.
Wouldn't it be like there's no like forces happening because it's just like the leftover like momentum from where they're going?
Okay, all right, so that's an interesting question. So let's think about, let me set up an axis. And let me just sort of mark the center point of, like on the line. This is roughly sort of where they collide. Okay, so if we have X and Y, if I do momentum conservation, I can say P system initial equals P system final. It's a quick collision and no external forces. So then I would say, MAVA plus MBVB equals, they're going to stick together, MA plus MB V final. I would say that VA here is just V naught I hat. VB here is, and with the MA is just M, MB is just M. VB here is minus V naught I hat. And so then that just gives me 0. So that tells me that V final is 0. And indeed, the center of mass is not moving after they collide. So where does the spinning come from? And spinning anyhow makes us think of angular momentum. Right? This ties back in with what we talked about on Friday, which is that a moving point mass can have angular momentum, right? We said L equals R cross P. So let me analyze this again from an angular momentum perspective. And let me say that this distance is d, when d is less than r, right? Because they have to hit each other. Okay, so then if I say there are no external torques, then I should have L system initial equals L system final. And so here I have LA plus LB. And then in the end, they stick together, form a single object and start spinning. So there'd be some I total and then omega. Okay. LA, I can do as RA cross PA. And LB as RB cross P. All right, I've called this distance D, this distance is also D, it's all very symmetric. Let me call this distance, what do you want to call it? We've already used D, right? X, yeah, sure, okay. So X, okay. So then for A, and I'm looking for the angular momentum about this point O. So for A, RA is pointing from O to the center of A. So that would be minus X I hat plus D J hat. Yeah. Okay, so it'll be minus X I hat plus D J hat. And then PA we've seen already is just M V naught I hat. That's in the positive direction for A. Okay. And then RB would be X I hat minus D J hat. And then crossed with the momentum of B is minus MV naught I hat. Any questions so far? Yes.
I'm confused why there's a J hat component. Is it just the distance?
Oh,
like,
to
it's just
the
the
R?
distance? Yeah.
Yeah, so we're doing the R from here to the center of the, yeah. Other questions? Okay, so when I do this cross product, what is I cross I? Zero, yes. I cross I is 0, and what is J cross I?
Negative K.
Negative K, yes. So I would get minus M V naught D K hat. And then here I would get the minuses cancel, M V naught D, and then again I have J cross I is negative K. So I'd get again minus M V naught D K hat. And this will be equal to my I total omega I. So I get minus 2 M V naught D K hat is equal to I total. And so we see that, to answer Yenta's question, we see that they are going to start spinning clockwise. And that tells us, yeah, L is pointing in the negative K hat direction. Right? If I found the angular momentum of each one, I'd say R cross P is into the board, or R cross P is into the board. Yes, I said.
Why does the J hat disappear, or I hat disappear?
Because I cross I is 0.
But when we do like I, J, and K cross I, J, and K, it's not
What do you mean I, J, and K?
like when you do the cross product of all of them together.
Yeah.
So why would one of them by themselves?
Well, no, I think what you're
Yeah,
missing.
maybe I'm-
Well, I mean, I think you're just missing that, like you will get an I component from other parts. So if you do, for example, J cross K, you will get an I component.
Okay.
Right,
Yeah.
so the I component doesn't come from other I components, it comes from like J and K components. Yes,
Wait, so we started with the momentum components being like I hat and J hat, so there, it's like
but the momentum
wait, sorry.
is in the I hat direction. But the angular momentum, even before the collision, was in the K hat direction, negative K hat.
Wait, sorry, can you say that one more time?
The momentum, P, the linear momentum was in the I hat and negative I hat directions.
Oh.
But R cross P, the angular momentum, was always in.
Oh, right, because also they're like, that like makes sense to me, because they're moving towards each other. Yeah.
So yeah, so this sort of gives us a physical reality of like, okay, what was the point of saying that a moving point particle can have angular momentum? It's like, oh yeah, no, because that allows us to then use angular momentum conservation. It's just like this hidden form of angular momentum becoming a bit more explicit and turning into the spinning form of angular momentum. Questions? Okay. All right. Let's see. Okay. One more question. Any questions about this? Yes.
Just want to make sure, so if you have two discs, scenario A is both the same, they have the, scenario A and B have the same moment of inertia. Then scenario A has, they're smaller, and scenario B, they're bigger discs, and scenario B will turn fast.
It's not just about them being smaller or bigger.
D is bigger.
D, I mean, that I just made it to make it clearer that they could collide but be off axis. The crucial point was in the first case, they were on axis. They were directly, like D was 0. They were just colliding head on, right? And if D is 0, you can see that, oh, they don't have an angle.
Right, I'm thinking the same scenario, just, the D becomes, the D in each scenario becomes bigger, so like you have a bigger
Okay.
disc there and bigger disc there.
Sure.
Then the angular velocity will be larger.
Oh, I mean, depends upon how I is affected as well.
I'm saying I.
If I stays the same, then yeah, if D is increasing and everything else stays the same, yeah. Oh, yes.
Did you use the position vector in that example just to demonstrate that the I hats cancel out, or is that something we should that be part of our setup anytime we're doing a cross product law?
So can you clarify that again?
Yeah, so you don't need the minus xi or the positive xi. on those
Oh, I see.
examples. Like all the other problems we've done on homework where you're using R, all you use is a distance, essentially just like a magnitude from the point where your axis is defined.
Right.
But why did you use the full position vector there?
Okay. So in a lot of the cases we've seen so far, your R and your F or your R and your P were perpendicular to each other, right? And so if you're looking at the magnitude, if you're doing like tau is equal to R cross F, we know that the magnitude of tau can be written as like either RF sine theta or as R perpendicular times F or as R times F perpendicular. And if they're already perpendicular, then this sine theta, this gives you sine of 90 is 1. And so you get the full magnitude times the full magnitude, right? If I wanted to do that here, so similarly, you could have R3 sine theta, R perpendicular times P, or R times P perpendicular. I would need to pick out the perpendicular component of one of the two, which you're right, I can do in this case. I can say that, oh, P is this direction, so I only need the component of R which is perpendicular to that, which is D. So you could do that, and that will get you the same result at the end. I just thought it was nice to sort of show the full cross products out, yeah. Does that sort of answer your question?
Yep. Thank you.
Okay, so one more question. Rotation. So we have a thin disc, which is the gray thing here, of radius r. It's spinning without any external torques on a vertical axis with a constant angular speed of omega naught. And then you drop a thin hoop on top. Give you some dimensions. Okay, and it's asking, okay, once they've finally settled into spinning together, what is the final omega one? And I would say you can go straight to discussion on this.
Yeah.
What's changing?
No. You're changing the eye. It's
The rotation inertia of the but the same factor should be our positions at grades, right? So like so if that so if that
I'm trying to find this formula, but wouldn't it change what you're doing now? The mass is 2m. Two moves is like.
Sure, yes, because.
I wonder which one is.
Yeah.
It's like.
I make.
I always
So.
In this point.
This and I for. So for this, it's 1/2 m.
So you have those together.
Yeah.
So momentum is conserved.
Oh, I said one being the I after the word.
Basically.
Oh, okay.
Nationally.
I feel like that's not a good.
Yeah.
That's a good,
Right. I agree.
It's like one more.
And then that's true. That's just like consider. It's like, whoa.
Yes.
Let's do something.
So again.
Oh, it's okay, so just MR. No, yeah, it's just, like, what about?
It is, yep, it is one step.
Cause it's gonna.
Yeah.
Imagine like a little.
I mean, 16. No, it's so what it's R.
Just solving for omega one.
Yeah.
No, this is like.
I mean, as long as you're comfortable with this equation. Are you comfortable with that?
Yeah, it's really the.
Alright, but just remember that the radius of the is different from the radius.
Right, shall we do like I1 omega 1 plus 1 half?
Yeah, I was just
scribbling, yeah, okay, all right.
Let's put that in mind.
So the 3/4
Yeah.
Okay.
But like, I feel like there's just so many options.
Okay.
I was like, yeah, I'll be waiting.
And like, I'm gonna like.
You get 1/3, yeah.
Oh, this is probably on the side.
Yeah.
Wait, and then you put it on the.
Yes.
I literally do.
I'm right, but it doesn't mean it's like, oh, you have kind of the.
Yeah.
And she does that all the time.
Like,
Yeah, that's what I thought.
I've never done it.
Basically, I know you pi is increasing in omega one increase. By the proportion that are
Add two things together.
Oh, wait.
Their inertia just.
The sum is on the same
And they
axis.
sound like, like they inform you that they're.
Okay. Alright, okay, so get ready, hopefully you reached an answer. Alright, show me what you think. Okay, mostly for C. I honestly don't remember the answer off the top of my head, but let's see if I you put the answer in the slides. Yes, I did. So this is a rotational collision, right? You can think of this as a rotational inelastic collision. And so no external torque, so angular momentum is conserved. So you have some I naught omega naught equals I1 omega 1. Initially, it is only the disk that is spinning. So you have 1/2 mr squared times omega naught. Afterwards, you have the combination of the disk and the hoop. So you still have the 1/2 mr squared for the disk. And for the hoop, you have m times the radius of the hoop squared, but the radius of the hoop is big R over 2. So you have that. And this combined object is spinning with angular velocity omega 1. So you can solve for omega. So yeah, all right. Oh, by the way, talking about collisions and such. Oh, question.
This is formula uses conservation as angular momentum.
Yes. Yeah. So yes, talking about collisions. Just a quick note about one of the problems on the last midterm. Where the last problem was there was the space probe that exploded, right? So some of you got it, some of you didn't get it. The crucial concept there is if you have an explosion, imagine taking a video of an explosion and then running that video in reverse. What do you see? You see an inelastic collision. You see things coming from different directions, colliding and sticking together, right? So an explosion is simply an inelastic collision in reverse. And so momentum will be conserved. Okay, kinetic energy is not conserved, right? Because you could start with an object which is at rest, and then once it explodes, it definitely has a lot of kinetic energy, right? So kinetic energy is not conserved. You have chemical energy being converted into kinetic energy, but momentum would be. Okay. Last bit for today. Yes, we just go to that whiteboard over there. I'm not really going to spend any time talking about this, but you'll get some practice examples in your homework. Static equilibrium, we've mentioned this briefly before. So if you have a structure that is not accelerating and not rotating, then you can say that tau net equals 0 and F net equals 0. These are two separate conditions. Usually that allows us to talk about civil engineering structures and figure out the various forces involved. And as a sort of example of that, you have this arrangement of wooden blocks, right? Each of these is, right? I just assembled them right now. You can see this last block is actually completely off the table. If you drew a vertical line, it's completely off the table. But the combined center of mass is basically right near the edge over here, right? Just slightly inward of the edge. And so that's why it's still stable at the moment. If I move it just a little too far, this one is still fine? Yes. Okay, then this one will start to topple. But basically, it depends upon where the center of mass of the system is. And if that's in a stable position, then your system is stable. Otherwise, it will start to topple. Remember that even though there's no homework this week, there is homework due after the break, and the homework has already been released. There is one final quiz, as I mentioned. Hopefully you saw my email. If you didn't, please check your email and read your email. And there's a quiz due today instead of last Friday. It was released last week. There's a quiz due today. Yeah, that's it. So that's a great idea. Something that all exceptions. I thought it was next to each other. But it is centered on something that is not
the total mass.
No, there's something inside, yeah.
I would give it, if I would give it to you, I would.
There's no directly touching the ground. Well, no, I mean, no, so what I'm saying is that actually this metal base, there's a
We
central
didn't actually
spike.
watch
It could be if there's
a
a
sad.
Sure, in that case, then there would be like friction grounds. Yes.
We need to hang out, but then also. That's what they say.
You guys.
No, I don't think it's touching the outside. It's only touching the.
Oh, but let's say it is, it doesn't matter if it's.
Container or not.
Well, in the case that it
You
is.
should have that.
Nah.
And then what about, like, there's a person standing here that doesn't look like one side.
Thank you. Thank you.
They're also friction.
Is that
A friction between what?
It is a,
Like a outstanding.
which,
Yeah.
begin the license
No, but
change.
you're part of the same system, so
Right,
we don't
it's
worry
not-
about.
That's what is really, so like the legal one is a lot harder.
So just to recap, if
Because-
this whole thing
Yeah,
was.
like.
You know what I
one
did?
thing,
You know what I'm
then
supposed to this week, right?
connected for whatever
No.
stable.
Yeah, exactly.
Frictures,
Yeah,
and
like,
then if it's
Doing
not,
it a month before
then-
turning two is like super,
Like, yeah.
doing it afterwards like super.
Hey.
That is correction for an should I give this to you now or does it that for you?
Oh, either one. All right, yeah. Okay.
Thank you so much.
Did you respond to my email? or-
Yes, I
Okay,
said anytime this afternoon.
I see. Okay, cool. Oh, in that case, let's just fix the time right now.
Okay.
would,
My only class is allowed.
I see, okay. Let's say 2:15?
That's perfect.
All right.
I'll see you in your office, right?
Yes, in my office.
Okay, have a good day.
Jersey.
In New
I will see you on-
Jersey.
General questions,
Yes.
one of inertia,
Yes.
like different shapes.
Yes.
You have to.
Yes.
Provide it.
No.
That would be
So
so.
we'll be given what
Yes.
we need. Oh, yeah.
Yeah, that was great. That was a great.
Almost at break.
I was gonna talk about.
Yeah.
So I just want to say, I would like this something
Okay.
I am admittedly not very happy with my expected.
Okay.
Um,
Okay. Hey, tell me what you do so well.
Well, I just looked at skills and shit before I started like that now and then trying to access. Over something like this, would I know what to do, or would I know?
And how do you do that knowledge?
I first write down the things, circle the ones where I'm struggling with it, and then I realized like that's what. Surround something like that.
Okay, that is a good start. I would also revise, I mean, like previous quizzes, problems on the Friday problem sets.
Okay.
And try and do them. It's not just about like, if you see the solution, do I understand them? It's like, could I reproduce this myself without them? Okay.
Yeah, that's.
Yeah. Oh, yes, yeah. So. I guess I'll just move. Yeah, claro, Ross.
See that.
Yeah, so I don't know what this.
I hope so.